let me introduce Mr. Satananda Burla. Satananda Burla is a senior principal engineer at Marvell, specializing in the research and development of cutting-edge networking and storage infrastructure solution tailored for AI, cloud, and enterprise markets. He actively represents Marvell in technical forums including OPA, Technical Steering Committee (TSC), Oasis Virtue, and also Ultra Ethernet Consortium (UEC), where he has contributed the development of the key specifications. So I request Mr. Satananda Burla to take over.
Been working with Marvell for the past 14 years, working on network infrastructure, architecture and design. Today I want to talk about evolution of Ethernet transport, why we need to evolve Ethernet transport for AI, and the need for reinventing RDMA and simulation infrastructure. Motivation. So let me first talk about what the problem is. So on the right side here, you can see a chart this is from Meta. This is about the time spent in networking in different training models that Meta had. And you can see the time spent in networking is well above 50% in one of them, and average is around 30%. So what this means is any optimizations you do in the networking are going to have equal effect of this percentage in optimizing your resources, whether it's training or inference, right? And then, so what is happening is the models are getting bigger, the AI models. We have trillion plus models now, and they are not fitting into one GPU parameters or the model anymore. So you have to have distribution, and with distribution you get communication and then the communication overheads. So the idea here is to see how we can optimize these communication overheads. So before I go into the details, let me just talk about how a typical ML training process works. So you have your neural network, which has your input layer, hidden layers, and output layers. And you start with some assumption of your weights for your model. You do a forward pass through the model, calculate the error, do a backward pass, and do a gradient descent for your errors, and keep doing that till you get your error into a closure, like it converges, the error converges to a value that's acceptable. So if you go into a training cluster, zoom into an AI training cluster, this is how it's going to look, right? You would have your storage nodes, your compute, and your management. The more important thing is the compute nodes here, the nodes that have your GPUs or XPUs, and then your NICs, and they are doing the bulk of the training. So as you can see, there are two kinds of fabrics here. There is a blue fabric that I drew between the GPUs, which is called a scale-up network, and then there is the yellow fabric that I drew between that's connecting them to the switches, which is called a scale-out network. So today the talk is probably going to be about the scale-out network. You have your scale-out today is mostly dominated by Rocky, which is RDMA or Ethernet. And we'll see what the problem with that is and how to address that. So here is an overview of what kind of communication patterns you can expect in an AI/ML cluster. So what we have seen so far with the training models is that this is mostly dominated by collective communications. Most of the communication is collective communications. We'll go into the collectives a little later. And one important distinction with the other data center traffic is that you have a lot of where you have data center traffic is where you have a lot of what you call entropy, where you have millions of flows or thousands of flows. AI is not like that. You have very low entropy, very less number of flows, and these flow patterns are generally predictable and repeatable. and then these flows are bursty. In time, if you see, they start and stop in a bursty way. And also these flows are elephant flows in the sense that once a flow starts, you are going to see MBs of data getting transferred at line rate before the flow stops. And then if we go to the requirements, like I said, the models are not fitting into one GPU anymore, so you need to scale up, which means you need to have thousands of interconnected nodes. And obviously, you need low latency, you need to finish your training as fast as possible, high throughput. We are talking 1.6, 800 gig these days. Okay. And high injection and bisection bandwidth. What that means is that your switches have to have high radix. You have to have a way of taking in high throughput into the switch, and also whether it's a class or a rail or some kind of topology that you're using. And the important requirement is that you have a very high bisection bandwidth. So like I said, I do a primer on the collectives thing. So collectives, if you have dealt with MPI in the past, you know these collectives are a way of gathering your data or doing operations on distributed data. So you have different kinds of, let's say you have data that's distributed across multiple nodes, then you can have different kinds of operations that you can do. One is a broadcast where you want to distribute the data to every node, or the reduce where you want to take the data from all nodes, do some operation on that, then distribute the result to all the nodes. And there are similar other ones. I don't want to go into the details, but you get the idea. So we said the ML training process needs to be parallelized. So what are the parallelization strategies? So here are a few strategies. These are not all, but I listed some of them, the most popular ones. So the first way you attempt to parallelize your training is you take your data sets, you split them into batches, and assuming your model and your parameters are going to fit in a GPU, you take your batch of data, train on a GPU, take another batch, train on another GPU, do that as much as you parallelize as much as you can, and finally at the end of the cycle you take the results. Now you have gradients from all of these GPUs, you sum and average those gradients and readjust your weights and keep doing this till you get a convergence, right? So that's the traditional data parallel. Now that only works if you have your model that can fit in the GPU and its parameters. But there is a better way to do it if your model fits but not your parameters, in the sense that let's say your parameters are too large. That's generally the case with most DLRMs, right? Then what you can do is you can shard your parameters. That you can, by sharding what I mean is you distribute your parameter sets between different parallel GPUs, and if you realize that all reduce operation is nothing but an all gather and a reduce scatter, so you can do something called fully sharded data parallel, which is here. That's fine. On the left bottom, you can see the fully sharded data parallel, where you can have your whenever the GPU has to do a data parallel, has to do its operation, it does an altogether of parameters from all the nodes. Does this operation, at the end you do a reduce scatter to distribute your gradients. So that's two kinds of data parallel strategies. And when your model is big enough that it doesn't fit your GPU, then you go into other strategies which are like model parallel. There are two types of model parallel. One is tensor parallel and other is pipeline parallel. Pipeline parallel is pretty easy to understand. Like you take your layers, you distribute your layers between the GPUs, and you have each layer forwarding the activation to the next layer and so on. So, and then there is tensor parallel, which is an intra-layer kind of parallelization where if you realize matrix multiplication, if I want to multiply a matrix A with B, I can take every column of B, multiply with A, and add the columnar values, and I will get the result. So the idea is you can parallelize this thing where every column of B goes into another GPU, and you can do this operation parallelly. And at the end you do an OR gather to get the result. So that's one kind of tensor parallel. The same thing can be done with the row as well. It's similar, but the idea is that you shard your matrix multiplication. Finally, there is a mixture of experts model. This is the kind of parallelization where in transformers you have your, if you know transformers, you have your feed-forward network in the encoder. So one of the problems with your feed-forward thing is the network is that it's very dense. So one option there is to use sparse models with experts, which are with the gating network before them, and the gating network decides which input tokens go to which expert, and these experts are expected to be sparse. So the idea of parallelization here is that you can run different experts on different GPUs, and that way you can get your parallelization. So these are not the only strategies. These are some of the popular ones. For example, there is a sequence parallelism, which is kind of tensor parallel, and they are coming up by leaps and bounds in research. So I'm not going to everyone. So this is a summary of what these parallelism models are, and what do they result in for networking. At the end of the day, what effect does it have in networking, right? So if you see data parallelism, you do it when your memory constraints are small, and the collective operations are all reduced, all gather and reduce scatter. If you do model parallelism, pipeline does not have any kind of collectives, but it does have a centrality of the activations, and obviously you have to have values. One problem with the pipeline is that there is a ramp-up bubble where you know that GPU 3, which is doing layer 3, cannot do anything till GPU 0 and 1 can ramp up. So that's generally a bubble that it can be addressed, but that's with the pipeline. And you will have a higher TTFT, which is time to first token. With tensor parallelism, it is better in terms of parallelization because you are getting better parallelization intra-layer, but the data transfer between the GPUs is very high, and typically you want to be it to be in your scale-up network only, not go to scale-out for this to reduce the latency. And obviously, based on whether you do column or row wise, you will reduce the algorithm quality. Hybrid parallelism is a realization that the above ones are not exclusive or mutually exclusive. You can do each one, you can combine them, and that's what hybrid parallelism is. So how are we evaluating AML network performance these days? So if we took traditional data center networks, we know we are always measuring GBPS and MBPS. How are we measuring AML network performance? So one difference here is AML network performance, we are worried about flow completion times. That is, you can take it as a RDMA send or a write operation. You would want to count the time that is taken from the first to the last packet of that flow. There is another metric that is coming up, which is JCT or CCT, which is job completion or collective completion time. That's like I said, the collectives. So we want to measure how quickly you can complete a collective. This is also becoming a new standardized way for doing performance measurement, but there are too many variables depending on the collective algorithm you choose and other things. So the outcomes vary, so one has to be careful. The other metric is the 99 percentile completion time, flow completion time, which is like measures the time taken for 99% of your flows. So it focuses on tail latency or highlights the performance of your slowest 1% of the flows. So these are the metrics we are using to measure. So RDMA innovation or rethinking RDMA. So like I said, we are when we do these communications, we are on the scale of network, we are essentially using RDMA. So it's a recap of what RDMA is for people who have not seen RDMA before. RDMA is just like where you have when you have socket or TCP or UDP kind of data transfers, you have your application filling a buffer, kernel taking that buffer, feeding into the network card, and network card sending it. So whereas in RDMA you have your application directly sending the data without the OS involvement or kernel involvement, and this is low latency and low CPU overhead. Rocky RDMA was initially done with the InfiniBand, and Rocky was an attempt to have IP InfiniBand works carried over Ethernet. There is Rocky V1 and V2, which is L2 and DTP based. So, like I said, Rocky was an attempt to retrofit IVU into Ethernet. So, what are the problems? So after a decade of this, we know what the problems are. So the Rocky has a congestion control algorithm called DCQCM, which is quantitative congestion notification. This has been studied extensively. I'll not go into the details, but suffice to say, it doesn't work. Right? And it is you have to tune it so much for it to work. Then Rocky has this requirement of ordered packet delivery, which is if you miss a packet in a sequence, you have to go back to the first missed packet. Even if you receive packets later, you cannot acknowledge them. And reliable connection setup is Rocky connection setup is a strange thing. You have to go through a connection manager, which is typically another protocol to set up your connections. It's slow and it's insecure. And then Rocky has something called queue pairs, like NIC has queues, receive queues, and send queues. Similarly, Rocky has queue pairs through which the application talks to the hardware. And for every application that needs to talk to the hardware, you need a queue pair, which is evident to say that there will be a scale problem as you scale the applications. Security in Rocky was an afterthought actually. They introduced the IPsec in Rocky V2. The problem with IPsec is it's expensive at scale. You need a lot of SA state storage. So that's another problem. And like I said, requires lossless network, and it is difficult to tune with a single vendor equipment. Forget multi-vendor equipment. Excuse me. So Ethernet and so we said Rocky is bad. So what do we do, right? So Ethernet offers you advantages of economy, scale, and multi-vendor ecosystem. So we do have to improve upon Rocky. So we need to adapt Ethernet to for AIML or staggering. So that's the right side chart shows you, like if you take Rocky versus Ethernet, like TCP, the green versus the purple line, you can see the magnitude of latency. It's a magnitude of latency difference. So how do we overcome Rocky shortcomings? So idea is use multi-pathing, use packet spraying, use your network or fabric to the fullest extent you can. Obviously, you need a flexible packet delivery order. You need modern congestion control mechanisms, whether they are like RTT based, telemetry based, or receiver based. You need end-to-end telemetry. You need to know which switch or which path in your network is congested, so you can avoid or reroute. You need scale. Obviously, you cannot be limited by queue pace, so you need scale. And we need a fast connection setup, ideally half RTT setup, connection setup, and teardown if you can. So these are the innovation efforts that have been going on in the industry. First one is working around the Rocky B2 issues using traffic engineering. That is like making sure your traffic does not experience congestion because you have engineered it so. And having topology awareness and having an application to the congestion control and not rely on Rocky's EC2CN. So Meta has done this in their data centers, and they have papers on how this can be achieved. And then the other improvement that was done was by Google called a Falcon protocol. Falcon is a Rocky plus kind of a protocol where you keep the Rocky semantics as such, but you change everything under. You use modern congestion control, telemetry, out of order delivery, and such. Falcon is an open protocol submitted to OCP. The third approach, which Ultra Ethernet Consortium is taking, is redesign everything from scratch at every layer. It would involve out of order delivery, multi-pathing, swaying, et al. All included in the protocol. The specs are nearing completion, not publicly available yet. So I also wanted to talk about communication optimizations other than RDMA. So this is something called GPU Direct. So we said the GPUs need to talk amongst themselves and amongst GPUs at other nodes. So when the GPU needs to talk to outside, it has to talk to the NIC. And one of the options for the GPU to make it faster is to use GPU Direct, which is there are three ways of doing it, called async and async KI as well. But the idea is that you do peer-to-peer transfers from GPU to NIC and not involve the host. And then in the async, you do transfer initiated by GPU itself, and in the async KI, kernel does everything and you avoid the host completely. And this is another optimization which is called in-network compute. This is for the collectives. So the idea here is that between the communicating nodes in a collective, there are always these switches, and if the switches can take over the aggregation or the arithmetic ALU operation, then you can reduce a lot of data movement. The right side chart here shows you how the data movement happens in for instance, I'll reduce a double recursive algorithm if you did not use in-network computation. If you use in-network computation, it's significantly reduced and you get better latency. NVIDIA has a protocol for this called SHA, and UEC is coming up with its own version as well. So I wanted to speak a few things about call to action, call to research for academia. So these are the areas of research interest that we have at Marvell, and even I would assume other industry players. On the scale-up and scale-out networks, improving the XPU to GPU to NIC connectivity. PCI is the slowest protocol of the day today. So can we change it to D2D, chiplet, die-to-die, chiplet? Then can we do seamless scale-up to scale-out transition? What I mean by that is now the GPU kernels have to deal with the fact that they have some scale-up connectivity and some scale-out connectivity. Scale-up is load store, scale-out is RDMA, descriptor based. So how do you seamlessly not have the GPU kernel worry about it, but you do it seamlessly under the hood, either using specialized converters, extender solutions, compiler generated RDMA, or whatever, right? That's a area of interest, research area of interest. Congestion control for multiplanar technologies. Multiplanar means the NIC has multiple ports to the fabric, and how would you achieve better congestion control in those scenarios? Obviously, traffic engineering, topology aware scheduling. These aggregated fabrics are also of interest. On the in-network compute, we have a greater need for standardization, modeling, and simulation. We need an IIC, in-network compute protocol that works across scale-up and scale-out. Standard control plane for setting up IIC, Sonic side or something like that. Simulation of IIC implementation for open source software switches like OVS, PPP, standardized telemetry and testing, etc. And then the next thing is fabric security. We need we need to secure scale-up networks. PCIe has IDE and MLNetSec is similar, but scale-up networks need to be secure in the future. We need fast and stateless security, half RTT connection setups and teardowns. Multi-tenancy and virtualization is something that has not surfaced in AI until now, and in future it will. We need open hardware and software, for instance something like NetFPGA implementing Falcon or UEC. That would be helpful to the community at large. And final slide is talking about the need for simulation. We need a software, hardware optimized code design for next generation to improve next generation hardware. Obviously, access to realistic workloads is expensive. Large models can only be run by hyperscalers as of today with one parameters. Academia and small players are at disadvantage. So, how can others participate? I would say simulation is the way forward. Yeah, so now I would like to, before I go into this, request Rinku to come and say a few words about simulation work that they are doing. Thank you. And if you have any questions meanwhile she's setting up, I can answer.
I have one question. So to support GPU direct, are you considering from the intra data center, within the data center, applications talking to GPU direct, or also maybe edge cases where the heterogeneous device still use the IoT transport?
GPU direct comes from the fact that you have NIC and GPU separate in data center because of NVIDIA today, right? But if you are making your own XPU for edge or even for data center, I would think of combining that so that you have a die-to-die kind of connectivity or chiplet kind of connectivity and not go through another protocol like PCIe, right? So for edge, I would think that the device you would develop for your edge inferencing or anything should have networking capability along with this gen.
What about transport? Where do you see the transport? Like TCP/IP implementations or Rocky?
So TCP/IP is not dead, obviously. TCP/IP has its place. TCP/IP, like Google has done something called TCP device mem, which is equivalent of GPU direct if you think of trying to place the TCP payload directly into a GPU buffers and vice versa. So yeah, it will evolve in its own pace, right? So, but yeah, like there are inherent problems with TCP/IP in terms of kernel getting involved in it. That's what I mean.
And do you think these run on the NIC or on the GPU? Because now earlier they are running on CPU.
Yeah, I think that thing is blurring in the sense that if you take the latest, I won't call it GPU, XPU, that's being made by hyperscalers and such, who are making their own stuff, they would not want to deal with another NIC or something, and they would have their own connectivity, external connectivity, whether that's scale up or scale out. Along with that, along with the SoC, or maybe a die-to-die or a chiplet kind of thing.
Okay. Well, any more questions?
Actually, I wanted to add to some of the answers. So on the TCP direct question, right? I mean, GPU direct is just a communication model that says I can land DMA into a target. The transport is irrelevant. The problem that you have is you cannot run Rocky on a Wi-Fi adapter. So you need something that's actually embedded in the protocol, and specifically RDMA Rocky requires the NIC to implement the transport protocol because the application is unaware. And that's the real problem. There is no Wi-Fi plus Rocky implementation, and if you did it, the things that he was talking about with respect to Rocky requiring in-order delivery is going to be very problematic because wireless networks are very, very poor when it comes to in-order delivery for guaranteed packet order. So the complexity, I think, here is, and we were talking about this yesterday in the car with Prashant, that one of the problems that you have to solve here, and this is an academic opportunity, is can you adapt Rocky or even TCP? GPU direct can be done on top of TCP. That's actually not a, in fact, we'll talk about it in a few minutes. It can be done. The implication is, can you have a Wi-Fi adapter that does it in a lightweight, cost-effective way? That's the real problem.
Thank you.
Sorry for the background. I hope I'm still clear a little bit. Thank you so much. I hope I have 15 odd minutes at least. Okay, thanks so much. So today I'm going to talk about the collaborative work with Marvell and with IIITD with Praveen, which we're working on, and so basically I'm going to extend to where Satananda stopped, that why simulation is important for AIML workloads. So I'll be talking about the hardware-software modeling for distributed ML workloads. And the research team includes Sumit, Arjun, Ramanjit from IIITD and me from IIT. So the question is that why is this simulation for AIML workload a complex problem? So as you can see, the entire distributed training design space comprises of 3 layers: the workload layer you see, the system layer, and the network layer, where Satananda has already talked about that the workload layer comprises of things like your DNN models could be different, and they would use different size of parameters, the operations could be different, the parallelization techniques could be different, adopted by a particular organization, the communication patterns, whether the communication is blocking, non-blocking, synchronous, asynchronous, it's a design choice to make. Similarly, the systems layer itself, how this collective mechanisms, collective patterns are implemented, that is also a design choice. So there are different ways in which these patterns are implemented. The topology, the logical topology is different. The architecture, the underlying hardware that implements it would be different. That means the compute design, the NPUs or XPUs, whatever we call, those have different architecture. The memory design could be different. So all of this is the design choice on the system layer. And also as part of the network layer, how do you implement the communication over the network is a design choice, as we've already talked about these words like InfiniBand, Rocky. There will be different protocols for communication. The hardware, the underlying hardware uses different flow control techniques, buffering techniques, etc. So basically the point I'm trying to make here is that the design space is extremely complex, and you may pick and choose things from this entire stack to build up your system. So the question, so this again, Satananda has talked about this complex space where we do have, sorry, this pointer is this complex space where we have this inter-GPU communication, we have communication outside the node. All this communication also uses different scale-up and scale-out techniques, like NVIDIA uses NVSwitch for scale-up and InfiniBand for scale-out, so on and so forth. And recently I talked to Srijit about Fabrica. They're coming up with their own scale-up, scale-out technique. So these techniques keep changing and the evolution is extremely fast. So the question that we want to ask is, can you predict the distributed ML training performance given this kind of a complex design space? So the question is, how do we model this design space? So there is an existing work effort that is going on from Georgia Tech by Tushar Krishna leading it, and what are they doing is they have come up with a tool called as Chakra and to model the workload layer of this distributed training design space. Basically, I'll be going into details, but what is exactly Chakra? It's basically a graph-based representation for ML workloads, which will include these layers. And another tool that they've developed is called Astrosym, which basically is a distributed AI system simulator. It simulates the system and the network. Now, what are their objectives? And so I'll be talking a little bit more on the technical angle. Could be a little boring, so pardon me for that. So firstly, why Chakra? Why do we need this graphical representation? And what are the objectives of Chakra? So as Satananda already mentioned, that running a full workload benchmark is an expensive operation. You need, for example, 25K plus nodes that are running in parallel and they communicate with each other. And none of us have this kind of an infrastructure except for the big hyperscalers. So it's an expensive operation. Also, as I talked about, it needs a software expertise as well as the hardware expertise. So there's a lot of cross-domain expertise needed. It is difficult to isolate, if you want to monitor performance, difficult to isolate the specific bottlenecks, difficult to split out behavior between compute memory and network. And also one more important thing is every organization has some proprietary models or proprietary software which they would want to hide. So then if you want to do the performance evaluation in such a case, it's harder to obfuscate this proprietary information. So what does Chakra do? Is basically what you want to do is you observe what happens in the production, observe the performance, reproduce this using some representative benchmarks. So Chakra would be helping us getting these representative benchmarks, design and evaluate this over a simulation platform which provides you all the multi-layer simulation platform, implement and test this and over a representative benchmark, deploy it at scale, again observe. So this is your co-design loop. And we can't do this on a full-fledged infrastructure because it's an expensive operation. Okay, feel free to stop me at any point if you want. Let's go to Chakra first. So what does Chakra do is, it provides a graphical representation. There are three components that, three types of nodes that represent the AI workload. So one is a tensor node, and second is a compute node, and then we have the communication operator node. So we have three types of nodes, and the edges in this graph represent the dependency between these nodes. So there could be two types of dependency. I'll go a little detail in it. Let me talk about it here itself. So there are two types of dependencies: control dependency and data dependency. So control dependency basically tells you the step-by-step operation that needs to be done, and the data dependency tells you that how much you have to wait for some data to arrive before you proceed with the operation of that particular node. So how does Chakra implement this? Basically, it provides a proto file where you have this node proto format, where I'll not go into a lot of details, but there is a node type for each node, and this type here represents, as I said, there are 3 types of nodes, but there is more granularity shown over here: the memory node, the compute node, and the communication node. And also they have defined one additional node called as a collective node. So if you want to represent a collective, you can have a set of collectives represented here. Another thing that additionally Chakra provides is you can add your own attributes. So, and for each attribute, you can define the type of attribute, that what is the data type of that particular attribute, and you can include your own attributes and implement in this Chakra system. This is one example Chakra trace. So there are 2 types of traces that Chakra provides. One, which is a CPU trace, which is also called as the host execution trace, or the other term is Python ET, that is Python execution, PyTorch ET, PyTorch execution trace. And you can see in this particular graph, if I take this subsection of this graph, you can see that this node, which is the PyTorch profiler node, it first calls, according to the graph, what it means is, first call this node, finish the operation, then go to the next node, barrier, then perform the all reduce operation, record the communication, record the communication. So basically this graph shows the control dependency, and here this particular subsection of the graph shows the data dependency. So this arrow is indicating that there is dependency. Whenever only this operation is over, we need to take the data from here, finish this operation only when this data arrives. So here we are showing the data dependency. This is the part of the Chakra execution trace, the CPU part of the trace. Because PyTorch is implemented in a subtle way, there are 2 types of traces required: the PyTorch ET trace, and there is something called as a kineto trace. This kineto trace basically traces the CPU as well as the GPU profile. So it's not very easy to find out what it is in details here, but basically it shows the timing when this particular section is showing the CPU thread, and the timing when this CPU is running and what operation it is doing, and this part of the visualizer is showing the GPU operations and for how much time is the GPU running. So you can have a visualization using this kineto trace. Now, finally, why I'm talking about this Chakra trace is this acts as an input for simulating our AI/ML workload. So the CPU trace itself is not enough, the GPU trace itself is not enough, we need a combination of both. So Chakra, basically this is a workflow that Chakra follows. You have your open source ML model, and PyTorch generates these 2 types of traces, PyTorch ET and kineto trace. The differences here are as follows: the PyTorch ET does not include GPU kernel information, and the kineto trace does not include information about the value, the shapes, the types, etc., and it does not have any information about the dependencies between the nodes. So there is a trace merger tool that Chakra has developed, which merges these 2 traces and provides you with a Chakra host plus device execution trace, which includes everything. But for simulation, you also need additional timing related parameters that need to be added. So there is another tool called as a Chakra converter, which modifies this JSON file. So all these 3 traces are JSON formats. This JSON file is converted into a proto file, which I was showing earlier, and this is your final post-process Chakra trace. So this proto file is now ready to be fed to your simulator. So the workload layer is now already in the form of a profile. I'll skip this slide in the interest of time. So I'm talking about the workload layer here. We finished that. So this workload layer by Chakra is represented as this final post-process Chakra IT, and AstroSim simulator will simulate the system and the network layer. I'll go into details later, but right now let's see the workflow of how AstroSim works. So it takes up this graphical representation which is in the protofile, and you provide the workload parameters. The AstroSim simulator basically reads this protofile, and based on the node type, it invokes the system layer. And its job of this, so for example, in this case, okay, so for example, this is a graph you see, where we have these nodes where there is some remote memory access, there is some compute and communication access, kind of an ET that I'm showing here, in execution case I'm showing here. The workload layer basically identifies what is the next issuable node. So let's just start with the remote memory node. And now to perform this operation, it will invoke the system layer. System layer may invoke network layer or not. And there is a callback to the workload layer. Once this particular node is implemented, this simulation is done. Once it is done, this node is freed using, the API is not important, but this node is freed, and then again identify which is the next node issuable. So basically a depth first search is done, and this Chakra execution trace is completed by the workload layer. Now, let's talk about the system layer. So, systems layer, the job of the system layer is to implement the collective algorithms, and it is implemented as a finite state machine. So, I will not go into the details of this finite state machine, but this is actually showing an order reduce operation, and the workload layer is invoked the system layer. System layer will perform tasks like send a message to a particular node, keep waiting for a message from a particular node, and this operation is once is done, this part indicates the reduce scatter, this indicates the all gather. When you reach the done state in your finite state machine, this particular operation is done. Once this operation is done, there is a callback to the workload layer saying that this operation is done. Internally, systems layer, for doing a send and a receive operation, will invoke a network layer to send a data. This is done. Okay, I think in the interest of time, let me just go ahead and just one last point for the network layer. The system layer invokes the network API, and there can be a number of network simulators that you can plug in. So one advantage of AstroSim is it's a pluggable framework. So you can have your own network simulator plugged in, your own memory simulator, and your own compute simulator plugged in. So for networking, there are 4 types of simulators available: analytical ones, on-chip simulator support, and NS3, which is for inter-network simulation. So I'll just quickly talk about what are we doing at IIIT Delhi. So we just started out and we are trying to identify what all can be done. So first question that we're trying to ask is, how does a network layer impact the ML performance? And towards that, one of the things that we're doing is we are modeling the network stack at the node level itself, which includes the host side and the NIC side. And after getting some insights from here, we also plan to go ahead and see the gaps in the AIML transport design and design a domain-specific AIML. The other problem that we're trying to address is, can we predict this AIML workload performance without having the access to the large infrastructure? So the most important problem which is being addressed, and there are panel discussions happening everywhere, one of them recently happened at SIGCOM, was that if you don't have the data, how are you going to predict and what is the meaning of that prediction? So if you don't have real data, there is no point. I mean, your prediction is not making any sense. So the question is that can we have a smaller infra and extrapolate the traces available from smaller infrastructure to get a large infrastructure trace? So some effort could be made towards extending this chakra execution trace. So this is the kind of work we are currently doing. I don't know how much do I have, a few minutes or no? 2 minutes. Okay, then I'll just quickly talk about just a few results that we have. So we modeled this NIC where the GPU to NIC communication involves a PCI switch, which will add some PCI latency, some NIC processing latency, and so on and so forth. So we did some initial results with the Chakra AstroSim framework. We ran the LRM workload over here for a training job, and this particular graph is showing that does ML performance depend on the characteristic. So we took two network cards examples, the ConnectX-64 NVIDIA ConnectX-64 and ConnectX-4 and ConnectX-6 cards, and the plot is showing that for two types of topologies shown here, what is the job completion time. So the inference here, we are not trying to carry out the inference that the job completion time for FastNIC is smaller, which we already know that the job completion time has to be smaller. But what are we trying to say here is that there is a need for adding additional attributes to a simulator framework for the NIC-related characteristics. So identifying what are the abstractions and what are the attributes that we still need to add to model a complete NIC. Second plot shows the job completion time under different congestion control algorithms used over the network, and the inferences show that almost these three congestion control algorithms, BCQC and HPC, are equivalent, but time takes more time. Just one last interesting result I would like to talk about is we thought that since the hardware is evolving so much, in future it is not going to be a case that the entire infrastructure is going to be a singular kind of infrastructure. There will be heterogeneous kind of network cards, switches, fabrics. We will never have a homogeneous infrastructure. So can we use the simulation framework to model a heterogeneous infrastructure and make some have some findings and then again reiterate, go back and design the system. So this particular result shows when there are various congestion control algorithms and the job completion time is the y-axis here. Here, this is showing the fast NIC, this is showing the slow NIC job completion time, and this is showing a hybrid NIC, where hybrid NIC is basically a combination of 6 ConnectX-6 and 2 ConnectX-4 NICs. So we observe that even if we have more than 50% of fast NICs, the performance of this setup is almost equivalent to a slow NIC performance. So I'm trying to say that why is the simulation platform important? If we have this kind of hybrid framework, then we may need to test it first before we get into the actual workload. I will not go into the details. We made some modifications to NS3 to get there. Just to summarize, what we are saying is running full workload benchmarking is expensive, and we need a multi-fidelity simulation infrastructure. What I mean is sometimes we need more details in the simulation, sometimes we need less details. Then how can we have such kind of infrastructure? And also generate realistic data sets without infra. And there are multiple open problems, and if folks are interested, then please reach out. Thank you so much. If you have questions, I'm ready to take questions. Thank you.
Back to that, if you don't just have a single monolithic model that's running on, say, a GPU, and you're distributing that, does Chakra trace simulate that and merge all the traffic and operations emanating from those distributed workload, the distributed model, or does it just assume a monolithic model?
Yes, it is. So I was not able to like go to the flow, but firstly you run your workload over the infrastructure, and from there, when the workload is running on the actual infrastructure, the PyTorch traces and the Kineto traces, the PyTorch ET and Kineto traces are captured when your workload is running on the actual infrastructure. So, for example, if I'm running it over a 8-node cluster, then I will have a trace of the 8-node cluster. And now I keep like evolving over that representative benchmark and then go back. So that is where the gap is. What I find is if your initial trace is on an 8-node cluster, you cannot do anything more than that. It's like you can only distribute over this 8-node cluster. So the question is, can you extend that trace itself to simulate over a larger infrastructure? So currently, this support is not available with Chakra.
You mean for extrapolating an 8-node cluster
Yes.
to say a 16-node cluster without actually
having the
tracing the
infrastructure.
systems? Okay.
Exactly.
Thanks.
I request Rinku ma'am and Satananda sir. Stay back. Yeah. And I also request Professor Bhimajan Reddy Tama and Professor Praveen to give the good.
Just wait. Just wait. Small. Just wait.